So let us revise quickly what we discussed so far in regarding the compact spaces. So first of all, the definition of compact sets is that a topological space X is compact if every open cover has a finite subcover. And we've seen some examples of compact and non-compact set. Then we discuss subspace when we call it is compact if it has the open cover, and if that open cover is by the sets open in X, then this cover has a finite subcover. That property is we need to show a subspace is compact. And we proved several results regarding compact sets, that every closed subset of a compact space is always compact. And every compact subset of Hausdorff space is always closed. So examples of Hausdorff spaces are the real numbers with standard topology, R cross R, that is R2 with standard topology. And we also have seen that the continuous image of compact space is always compact subspace of the codomain Y. So Fx is a compact subset of Y whenever F is continuous and X is compact. So we have seen that with respect to cofinite topology, every unempty set is always compact. And in particular, every finite set is compact with whatever topology we take on that set. So we have seen a tube lemma, that is if we consider the product space X cross Y, if we take any point P in X and assume that Y is compact, that is the second component, and whenever we take open set W which contains this set singleton P cross Y, there is always exist open set U such that U cross Y is subset of W. So we use this tube lemma for this particular results, which says that if X and Y are two topological spaces which are compact, then X cross Y is compact. So here we are taking the product of two sets X and Y, but in general, if we know what is the meaning of arbitrary product of sets, the collection may not be finite. So if X alpha is a collection of topological spaces where each X alpha is compact, then the product of X alpha is also compact, where the collection X alpha is infinitely many sets, collection of infinitely many sets. So that result is known as the Tikhonov theorem. So which, if possible, we will try to cover in this course. But for that, I need to define what is the product of arbitrary collection of topological spaces. So we'll see that later. And we have seen this particular corollary that of this theorem, that if X is compact, then X cross X n times is also compact with respect to the product topology. And we have seen the automatic continuity of the inverse map. So this theorem says that if F is a bijective continuous function from a compact space to Hausdorff space, then it is the inverse is always continuous. That means F is a homeomorphism. So I think this is what up to this we discussed in the last lecture. So today I want to take a simple example from the real analysis. that the closed interval 0, 1 is a compact subspace of R with respect to the standard topology. On R. So we want to prove this, we want to show this example that it is a compact set. So closed interval 0, 1 is a compact subset of the real line. So whenever we want to show that some subspace is compact, we start with a collection of open subsets of X, and we cover that space that is a covering of the given set, and then we try to find a finite subcover. If we can do that always, then that means the set is compact set, otherwise it is not. So let us start with a collection U alpha. So this is a let U alpha be a collection of open subsets of R such that it covers the given set. So that means it covers so union of U alpha covers closed interval 0, 1. So U alpha is a open cover of 0, 1. We want to show that 0, 1 is a compact space. So that means we want to find a finite subcover of U alpha which covers the closed interval 0, 1. So to show it covers closed interval 0, 1, let us start with a particular set S, which is the set of all elements X in closed interval 0, 1, so that the interval 0 to X has a finite subcover of U alpha. So what it says is that I will start on the real line. I will start with so I'm given the interval 0 to 1. So I will start with any point X which is bigger than or equal to 0, and I will consider the interval 0 to X, and whether it can be covered by this finitely many U alpha. So if I can do this for every X which is bigger than 0 and up to 1, then essentially if this set S contains the closed interval 0, 1, that means 0, 1 will be covered by finitely many subsets of finite subcollection of U alpha, and that is what we want to prove, that closed interval 0, 1 is compact space. So therefore we are considering this particular set. So the set X contains those elements X between 0 and 1 so that the closed interval 0x is covered by finitely many U alphas. So that means closed interval 0x is a subset of union of U alpha k, where k running from 1 to n for some n. So let us first see that whether this set is non-empty or not. So observe that zero belongs to closed interval 0, 1, and the closed interval 0, 1 is a subset of U alpha. So that means zero belongs to union U alpha. So 0 belongs to unions U alpha. That means it must be in some of the U alpha, right? So therefore, there exists some particular there exists let us say G, which is a natural number such that U alpha J contains 0. So that means 0 belongs to U alpha J. So this means what? This means that singleton 0 is a subset of U alpha J, right? And what is singleton 0? Singleton 0 is closed interval 0 to 0. So that means the interval 0 to 0, so basically we are taking x equal to 0, is has a finite subcover of U alpha. Alright, in particular we are taking only one set here. So therefore 0, 0 is has a finite subcover of the collection U alpha, and therefore 0 belongs to the set S. So let us go once again. What is the set S? So the set S is the points x including 0, 1 and in between 0 and 1 such that, so basically x belongs to closed interval 0, 1 such that the closed interval 0 to x is a subset of, so has a finite cover means what? This is subset of union of U alpha L, where this union is finite, right? So in particular, when I take x equal to 0, I have found only one set here. So that is union of a single element. So 0 belongs to S, that means S is a non-empty set, right? It contains at least one element. And so now since S is non-empty and 0 belongs to S, that means in fact it will contain some positive x also. So now 0 belongs to S and 0 belongs to U alpha J, and U alpha J is open. Alright, so open subset of R, and if I have a point inside that set, that means it contains some basic open set. So it contains a neighborhood, right? So therefore there exists x greater than 0 such that 0 belongs to minus x to x. So usually we get okay, so we get the open interval AB here. Let us take arbitrary element. So since U alpha J is open, therefore there exists open interval AB such that 0 belongs to open interval AB, and which is subset of U alpha J. Alright, every open set contains basic open set which contains the point. So that is definition of basis. And What this means is therefore B is greater than 0 because 0 belongs to open interval AB. So B is on the right side of 0. So what does this gives is that the interval close 0 to B is subset of U alpha J. Alright. But what we want, if I want to show some positive element belongs to S, I cannot show that, I cannot take that element of S to be B, because for that I need to show the closed interval 0B is contained in finite union of U alphas. But what I will do is I will half B, so then I will get the interval 0 to B by 2, which is subset of 0 to B, which is subset of U alpha J. So finally what we get is, we get the interval 0 to B by 2 is covered by finitely many U alphas, and B is greater than 0, right? So therefore B belongs to S. So why B belongs to S? Because the interval 0 to B by 2 belongs to S, right? Because the interval 0 to this point is covered by finitely many U alphas, right? So therefore this particular interval is this particular point, whatever comes here, belongs to S. And what is important here is that point is positive, right? Since B is positive, B by 2 is positive. So what we have proved is therefore there exists X greater than 0 such that X belongs to S. So not only 0 belongs to S, but we can always find a positive number which belongs to S. So let us go to that diagram. So now we have found one positive X which also belongs to S, and 0 also belongs to S. So the question is how many such positive elements we can select, which is the largest X between 0 and 1, right? What is the largest one? So for that what we will do is we will take the supremum of set S, right? Because S is a non-empty set, so it always contains a supremum. So that will be the largest X which belongs to S. So since S is non-empty, we can non-empty set, we can define X naught, which is the supremum of X. X belongs to S. So now question is that whether X naught belongs to the set S or not. So claim, we will show that X naught is element of S, right? So what is X naught? X naught is the number such that the closed interval X naught is supremum of the X such that the closed interval 0x is covered by finitely many U alphas. So what we know about X naught is that it is supremum of X and every X is between 0 and 1. So therefore, since each X belongs to S, satisfies is element of 0 1, right? Every element of S is element of closed interval 0 1, and X naught is supremum of such X So therefore x naught is also belongs to close interval 0 1, because close interval 0 1 is a closed set, so it contains its supremum, right, maximum value. So now x naught is in close interval 0 1, and once again close interval 0 1 is covered by u alpha. U alpha is open cover of close interval 0 1, so therefore we can find gamma greater than 0 such that x naught belongs to this union. So again x naught belongs to some u gamma, right? So we want to show that x naught belongs to S. That means we want to show the close interval 0 to x naught and 0 to x naught is covered by finitely many u alphas. So for that purpose we found x naught belongs to some u alpha, that is u gamma, and u gamma is open subset of R. Right. So what we get is we again get an basic open set which is which contains x naught. So we get an epsilon greater than 0 such that the interval, so this is basically the epsilon neighborhood around x naught point, and it is contained in u gamma, right? So if I have a point x naught and if I have open set u gamma which contains x naught, it may not be symmetric, it can be like this also, right? It may not be centered at x naught, but in any case I can always find a small enough epsilon such that x naught minus epsilon to x naught plus epsilon, this basic open set is contained in u gamma. Right, and so from this what we get is x naught is a supremum of S. So now x naught is a supremum of S. So every supremum we can consider as a limit of a sequence of the elements of S, right? If I have a supremum of a set, then I can always find a sequence of elements of S which converges to that supremum. So since x naught is supremum of the set, there exists a sequence xn of elements of the set such that xn converges to x naught. So here xn belongs to S means the interval 0 to xn is covered by has a finite subcover. Right. So this set is finite subcover. So that means xn converges to x naught. It means if I take any neighborhood, epsilon neighborhood of x naught, then I can always find a point from the sequence which is contained entirely in that neighborhood. So this is such neighborhood, x naught minus epsilon to x naught plus epsilon. So if I have a sequence which converges to x naught, then I can always find a point which is in the epsilon neighborhood of x naught. So that is a convergence of the sequence, right? So since xn converges to x naught, so there exists a point m belongs to n such that x naught minus x2 xm less than x naught, right? So basically we are taking here the left side of the neighborhood because x naught is the supremum. So therefore we have a sequence which is coming from the left side, right? So there exists xm, and here xm is element of S. Therefore the interval 0 to xm is has a finite subcover of U alphas. So now what we got is that we got x naught xm belongs to, note that xm is element in the interval x naught minus epsilon to x naught. X naught minus epsilon to x naught is subset of x naught minus epsilon to x naught plus epsilon, and this interval is a subset of u gamma, right? X naught minus epsilon to x naught plus epsilon is a subset of u gamma. So what we got is this interval xm belongs to u alpha, and x naught is also in u gamma, right? So what we get finally is that I have x naught minus epsilon and xm. So both of these belongs to u gamma, so that means the interval xm to x naught, this closed interval, is a subset of u gamma. And on the other hand, I have got another closed interval which is covered by finitely many u alphas. So when I take union of these two sides, then it is also covered by finitely many u alphas, right? Because finite union of finite sets is also finite. So therefore 0 to xm union xm to x naught, which is equal to 0 to x naught, has a finite subcover. So this, we have shown that this closed interval, which is starting from 0 to x naught, has a finite subcover, and that is exactly the condition of the set S. So the condition of the set S is that the element 0 to x, right, has a finite subcover, and that element should be in closed interval 0, 1. So we have found the point x naught, which is in closed interval 0, 1, and it is also covered by the interval 0 to x naught covered by finitely many u alphas. Therefore, x naught belongs to S. So we found that x naught belongs to S. So that was our claim. So we proved the claim that x naught, which is a supremum of the set, which belongs to the set itself. Now, what we proved is that x naught, which is supremum of x belongs to S, is this x naught is element of S, right? So now what is S? S is the set x belongs to close interval 0 1, such that the interval 0 to x is covered by union of u alpha k running from 1 to n for some natural number n. So that is basically the meaning of 0x is covered by finitely many u alphas. So now the thing is x naught, which is supremum of the elements of S, that is also belongs to S. So question is if x naught is 1, then that means that x naught is supremum. So that means the interval 0 1 is a subset of S, and S is subset of 0 1. So that means S is exactly 0 1. So we are done. But on the other hand, so S is 0 1 means 0 1 is covered by therefore 0 1 is covered by finitely many u alphas, right? And that will give us 0 1 is compact. So if x naught is 1, x naught is the point which is between 0 and 1. So if x naught is 1, then we are done. The next case is that if x naught is not 1, so x naught is the point in the closed interval 0 1, and if x naught is not equal to 1, that means x naught is less than 1, right? So x naught is a point in the closed interval 0 1, and x naught is is less than 1. Then once again we can find, and so once again, since x naught belongs to 0 1, which is covered by u alpha, so there exists some so we have already noted there exists gamma greater than gamma, so that x naught is in u gamma, and since x naught is in u gamma is open set, so we can find the neighborhood of x naught. So x naught minus delta 2, x naught plus delta is contained in u gamma, right? And that will once again will give us so this will give us the interval x naught to x naught plus delta by 2, let us say, which is subset of U gamma, and we already know that X naught belongs to S. So X naught belongs to S means this interval is contained in union U alpha J running from 1 to n. So this has already finite subcover, and this is also covered in one open set. So that means union of these sets 0 to x naught plus delta by 2 is contained in U gamma union U alpha J. So this is again finite subcover of U alpha, right? So finally what we got is that this interval is covered by finite subcover. That means x naught plus delta by 2 is in S. But this is a contradiction because delta is greater than 0 and x naught is less than x naught plus delta by 2. So x naught plus delta by 2 cannot belong to S. Why it cannot belong to S? Because x naught is supremum. If you have supremum, any number bigger than that cannot be the set element, right? So that is a contradiction, and this contradiction is coming from our assumption that x naught is less than 1, right? So this is false, right? So this assumption is false. So this case cannot happen basically, right? So therefore x naught is always 1, and x naught is 1 means closed interval 0 1 is compact. So this is essentially the proof of this small example that closed interval 0 1 is the compact subspace of the real line. And what we proved in the last lecture is that we have two compact sets, then its cross product is also compact set. So that will give us another example. So since closed interval 0 1 is compact, subset of R, so R with the standard topology, right? What we get is that we get from a known result that the cross product x cross y is also compact. So here I'm taking the same set x and y is same, which is 0 1, close interval 0 1. So 0 1 cross 0 1 is compact. Compact subset of subspace of of R cross R. R cross R is R2 with respect to the product topology on R2, and here note that what we have proved earlier is that the product topology on R2 is the topology nothing but the standard topology. All right. So 0 1 cross 0 1 is a compact subset of R2 basically that we are getting here. So what is the diagram of 0 1 cross 0 1? That we already know that in if we take R2 xy plane, then 0 1 cross 0 1 is nothing but a square which contains all these points, right? So what we have just discussed is that this set is a compact subset of R2. So that is a 0 1 cross 0 1 set. But another example is that if I take the set Y to be the closed unit disk. So closed unit disk means x comma y. So that x square plus y square is less than or equal to 1. So the shape is shape of so this set in xy plane. When we draw, we know that this is equation of circle, and so basically it is inside circle, inside the unit circle. All right, it is radius 1, center is origin. So this set, don't confuse with y-axis. If you want, we can denote by d because it is open unit disk. So this is basically all the points in this set, that is d. And note that we cannot write d as x cross y because it is not of the form rectangle, right? So d is not the product of x cross y, so we cannot use this particular result to show that d is compact. But we use another criteria that every closed and bounded subset of real line is compact. So that result is known as Heine-Borel theorem. So we will prove that result in the next lecture for the topological species.